All right, so I'm going to go over a couple of problems from the impulse practice problems that I think were a little bit tricky. I'm going to go over 8 as a model for the spicy problems and 11 as a model for the V-spicy problems. And then I'm going to go over all of the questions in the study guide as you guys prepare for your test tomorrow. Okay, so for the impulse practice problems, so I was going to go over problems 8 and 11. So let's take a look. So for problem 8, for all of these problems, the first thing I want to do every time is just write impulse is equal to m times delta v is equal to force times t. Where did I get this? Oh, it's not on this page, but it's just it's a formula for impulse. Momentum times change in velocity is equal to force times time. Now, what I want to do is make sure that for every problem, I'm taking note of any important variables. So here I have a group of people are pushing a stalled car with a mass of 1,100 kilograms, that's mass. They push with a net force of 350 newtons, so that's force, 10 seconds. What is the car's final velocity? Vf. Stalled car initially has a velocity of 0. We want to figure out what Vf is. Mass is 1,100, and the net force is 350, right? And so we want to figure out the car's final velocity. If it starts at 0, then the change in velocity is just going to be the final velocity, right? So let's see. So let's find the change in velocity is equal to the force times the time divided by the mass, right? All I'm doing here is some algebra. I'm doing that to get to this. So then the force is 350 newtons, the time is 10 seconds, and the mass is 1,100 kilograms. We end up with 350 times 10 divided by 1,100, and we get 3.18 meters per second. Okay, cool. That looks like the correct answer for number, what is that, 8? Cool. Now, for number 9, I'll do number 9 too, because 9 is a little bit spicier. So a 40 gram super ball strikes a wall with a velocity of 10 meters per second that is normal to the wall. It just means perpendicular. It bounces away at a velocity of 7 meters per second, still normal to the wall. What is the ball's change in momentum? If the bounce lasted 0.1 seconds, what is the force between the ball and the wall? Okay, this is a really tricky question because it requires you to think about the momentum being in 2 different directions, right? And so we know that the ball bounces, hits the wall, and then bounces off, right? So initially it is a velocity, we'll call this positive, and we'll call this negative, right? So the initial velocity is 10 meters per second, and the final velocity is negative 7 meters per second, right? Because initially it was moving to the right at 10 meters per second, and then if it bounces away at 7 meters per second, it's going to bounce in the other direction. So that's going to be negative 7 meters per second. So if we want to find the change in momentum, we need to use the change in velocity here. So the change in momentum, which is the impulse, is going to be the mass, which is 40 grams, or 0.04 kilograms, because I want to be using kilograms here. 0.04 kilograms times the change in velocity here. So if it goes 10 to 0 and then 0 to 7, that's 17 meters per second. We do V final minus VI to do this too. The final velocity is negative 7. The initial velocity is negative 10. So then it's 0.04 times negative 17. So the change in momentum is actually negative 0.68 roys, or kilogram meters per second, because it changes that much momentum going to the left. Now, the bounce lasted 0.1 seconds. Sorry. What is the force between the ball and the wall? Okay, so we know that the change in momentum is negative 0.68. Mass times delta V is equal to force times t. This whole thing is negative 0.68, so we can solve for the F. Over time. Time is 0.1 seconds. Negative 6.8 newtons. should be, the answer says negative 0.68, it should be negative 6.8. Oops. Alright, now you can use this problem to solve problems 10 and 11. Another good example is problem 11, actually. Actually, I'll do number 12, because for all of these, we have to just use the same formula, mass times change in velocity is equal to force times time. But whenever you're trying to find the velocity of something, how fast is it moving, what is its final velocity, if you're trying to find a velocity right over here, you know that you need to use all the information here to solve for delta v. Right? Delta v will be equal to f times t over m. And once you've gotten this formula from the original impulse equation right up here, once you've gotten this formula, you know that you can plug in whatever force you have, multiply whatever time times whatever time you have, and divide it by a mass. So you have some force over some time that's increasing the speed of an object, but then this mass is going to divide out, like you're going to take there's going to be some inertia that object has. So all of that force isn't going to go directly to its velocity, it's going to be divided by the inertia, right? And so let's do this problem as an example. A loaded barge has a mass of 1,500,000 kilograms and is traveling at 3 meters per second. The tugboat applies an opposing force of 1,200 newtons for 10 seconds. What is its final velocity? Alright, so let's see. Delta V is equal to the force, right over here, 12,000 newtons times 10 seconds divided by the mass. So that should say the change in velocity is 0.08 meters per second negative, because it's an opposing force, right? So tugboat applies an opposing force of 1,200 newtons for 10 seconds. What is its final velocity? So the velocity change is negative 0.08 meters per second. Then we know, and the initial velocity was 3 meters per second. Then that means that the final velocity is going to be 3 meters per second minus 0.08, so 2.92 meters per second. How long will it take to stop the barge? Well, it's going to take as long as it takes for the final velocity to be 0, or for the change in velocity to be exactly 3. So we need to say, alright, delta V is equal to force times time over m. We need to figure out time, and so t then is the unknown variable, so then t is equal to m times delta V over f. In this case we have the mass, and I'm not going to do the math, I'm just going to write it out over here. We have the mass 1.5 million, and then we have the change in velocity, because it has to go down to 3. It has to go down by 3, so negative 3 meters per second, and the force is going to be the same thing, 1,200. So then 15 times 3 divided by 1,200 says that you're going to need, it's going to come to a complete stop after 375 seconds, which is a long time. That's a long time. Now, how much force would a tugboat need to apply to stop it in 1 minute? That means now that we're solving for f, so we do the same thing, but we arrange the variables here for f. So how much force would a tugboat need to apply? We have the same equation, m times delta v is equal to f times t. It's just now that f is equal to m times delta v over t, and t is 1 minute, delta v is 3 meters per second, and m is 1.5 million. So basically all of these problems are just a matter of using this equation and then flipping it around a little bit. I'm probably not going to give you any I might give you one VV spicy question as a multiple choice on the test. But it won't be, this isn't going to be a lot of what the test is like. So make sure that you show your work for all of these, and if you want to get that 4 out of 4, you got to submit your work for all the problems and submit it. Alright. Now, for the study guide. Fill in the missing places in the table below. So the velocity of the variable is meters per second. Standard units are Oh, whoops. Meters per second are the standard units. The variable is V. What am I doing? Variable M is for mass. Standard units are kg. Sorry, I mixed those up. Newtons are represent force. Variable here is F. Roys is momentum, represented with a variable P. Change in momentum, aka impulse. The variable is delta P, change in momentum. And the units are the same. Roys are kilogram meters per second. And now total momentum is the same thing, P total. Just call it that. And that is the same, the units are the same as Roys. So the equation for momentum is just P is equal to M times V. Remember, it's a vector, so it has to have direction. The total momentum, P total, is just going to be equal to P1 plus P2. This isn't a real equation, it's just trying to remember that you have to add any of the momentums in a system to find the final momentum, and we do have to keep in mind the direction. So I'm going to add in those arrows, because if you're adding a negative momentum, you're going to subtract that momentum, right? So direction matters. Conservation of momentum says P initial is equal to P final. Okay? P initial is equal to P final. The impulse is that the change in P, which is generally mass times change in velocity, so this is impulse, the change in P, is equal to force times delta T. This is impulse. Really useful if we want to do if we want to figure out the change in velocity of an object, mass and time and all that good stuff. Alright, so for section 1, finding the momentum of an object, all we have to do is really just use P is equal to M times V. So in this case, the momentum is the velocity is right here, the mass is right here, so P is equal to M times V. The mass is 4.8 kilograms, V is 13 meters per second, so the momentum should be 62.4 R to the right. What is the rocket ship's velocity? Okay, so P is equal to M times V. We know that we want to figure out V, so V is equal to P over M. In this case, the mass is 110, the momentum is 2,200 kilogram meters per second up. We want to find the velocity, so if the momentum is 2,200 roys up, the mass is 110, then the momentum, or the velocity, will be 20 meters per second up. So remember to include magnitude and direction. Magnitude and direction. Okay. Car driving 45 meters per second along the highway and has a mass of 1,000 kilograms. A truck with a mass of 3,000 kilograms is also driving. So we'll call this V1, M1, M2. In order for the momentum to be the same, how fast must the truck be moving? So this, what is the velocity of the truck, basically? So then we know that if P car is equal to P truck, we know that P car is equal to the mass of the car times its velocity. The mass is 1,000. Its velocity is 45 meters per second. So the momentum for the car has to be 4,500 roys. Now, if we want the truck to have the same exact momentum, then P truck must equal 45,000 roys, and that must equal the mass of the truck times the velocity of the truck. Now we know that we have a mass for the truck, but we don't have a velocity. So let's see, V truck is equal to 45,000 roys divided by M, right? And here M is going to be 3,000, because we know what the mass of the truck is. So then the velocity of the truck should be 45,000 divided by 3,000, which gives you 15 meters per second. This truck needs to move at around 15 meters per second to have the same momentum. Alright. If you have two objects in a system, each with their own momentum, explain how you find the total momentum of the system. Add the individual momentums. This is basically a verbal explanation of the formula right up here for total momentum, adding the individual momentums. All right. This is all I'm asking you to do now is, okay, so you found the momentum of one object. Now what can you do with multiple objects? Draw pictures with vectors. This is going to help you with directions, okay? Small monkey is moving with a momentum of 40 kilogram meters per second to the right. Little monkey. So P is 40 r to the right. A large monkey is also moving to the right with a momentum of 80 kilogram meters per second. So P is equal to 80 roys. So if they're both going in the same direction, they're going to add. P total is equal to 40 P1 plus P2. We'll call this P1, P2. 40R plus 80R is equal to 120R right. Make sure that you always remember the direction as well, because that's super important. Okay, system includes a football running back and a linebacker. A football running back has a momentum of 260 kilogram meters per second. Okay, so P is equal to 260 R. A linebacker has a momentum of negative 120 kilogram meters per second, so this is in the other direction. So P is equal to negative 120 R, so it's the opposite direction. P total is then going to be equal to the sum of these two. It's just that now this one is plus minus 120R. Alright, so then we end up with, oh my god, do I really need a calculator for this? 140. 140R left. 140R to the left. Alright. Oh man, I am so odd. Alright, speaking of odd, for number 7, the total momentum in a two-object system is 90 roys right. One object has a momentum of 30 roys right. What is the momentum of the other object? Okay, so in this case, the two objects have momentum of 90 r to the right. And if one object has momentum of 30 roys to the right, then you know that the other object has to have, in order for the total of these two to be 90, the other one has to have 60. You guys can do that. It's easy money, right? That's P total is equal to P1 plus P2. Now, the total momentum in a two-object system is 100 roys to the right. One object has a momentum of 175 roys to the right. What is the momentum of the other object? Okay. So now P total is equal to 175 r to the right. P1 is equal to 100. Oh, I messed this one up. Whoops. Object 1 has a momentum of 175 r right. P total is equal to 100 right. Whoops. So if P total is equal to P1 plus P2, and the total is 100 r, and P1 is equal to 175 r, P2 needs to be negative 75, right? The only way this is possible is P2 is equal to negative 75 r. Negative 75 r or 75 r to the left, right? Either way. If the second object's mass is 4 kilograms, what is its velocity? So if it's P is equal to m times v, and P is 75r, negative 75r, and the mass is 4 kilograms, velocity is going to be equal to 75 divided by 4. For 4, so v is equal to 18.75 meters per second left. Calculate the total momentum in the system shown. Careful of direction. Okay, so then this momentum is equal to mass times velocity, 30r. Momentum here is equal to mass times velocity, but the velocity is negative, so negative 8r. So P total is equal to 22r. And I'm just going to say 22r right. In this case, P total is equal to, or P1 is equal to 5r, P2 is equal to 20r, P total is equal to 25r. Right, because you just add these two. Easy. State the law of conservation of momentum. Draw before and after extra vector. Good. Momentum will be conserved. This is straight from your notes. Momentum will be conserved in the absence of any external forces. So as long as we don't regard friction or air resistance, Momentum is always going to be conserved. Two cars are heading towards each other. The total momentum of the system before the collision is 487.5 kilogram meters per second. What is the total momentum of the system after collision? Momentum before is going to be equal to momentum final. So as long as there's no external force, which there isn't, total momentum afterwards is going to be equal to the same thing. It's going to be 487.5 kilogram meters per second, or ROI. It's going to be the same. Find the velocity of the truck after the collision below. So before, so P total is equal to, this is the only thing that's moving. So the total momentum in the before is based solely off of the big old truck. It's going to be the same here. Now, if this guy has momentum $1,500 or 15,000, sorry, then if the total is 30,000, then this guy also has to have a momentum 15,000 for it to add up, because that has to add up to that to get to that, because this is the same, right? Now, if the momentum is 15,000 and the mass is 3,000, we know that P is equal to M times V. V is equal to P divided by M. So we have 15,000 R divided by 3,000 kg. It's going to be equal to 5 meters per second. All right. What I'm going to do is make another video with the solutions to these 4 problems, because now it's advisory, and I have time right now.